Okay, so I should start, right?
Yeah,
So I'm going to share my screen. I'm not used to Zoom. I'm used to
you can
Teams.
that bottom you will have a share screen green option.
Oh, green option. Okay. Okay. I think that's the one I want. Can you see
Yeah,
can
it
you
is
see it?
coming.
So I'll put it in
Yeah. Now
presentation mode.
you can put on full screen mode.
Right. So is that good?
It is, yeah, now
Everybody
it is.
okay?
Yeah, it is
Oh,
okay.
okay. So going to talk about modeling wave-ice interactions in 3 dimensions in the marginal ice zone. And first of all, the photograph is taken from a field experiment 8 years ago, almost 8 years ago in October. It was led by Jim Thompson from University of Washington, and he will be speaking after me. And also it was co-led with Maddie Smith, and she will be also speaking after me. The photograph shows ice flows and ice wave instrument in the ice. So my co-authors are Mike Mylan, Ash Delaney, Mike Casey, and Young-Chen Hu. And so here's an outline of what I would talk about. I will not talk very much about theory because it's in publications. I'll give you results. I'll talk about a little bit about properties of the model, field experiment, and results. As you can guess, I've been working on this project for part-time for a few years, and part of the reason to join this workshop was to motivate myself to get that paper done with Mike. I'm sure he hasn't forgotten. Okay, so let's see what we've got here. So how to model propagation of waves and scattering of waves in the marginal ice zone. So 6 possible models, and these are documented in the 2 papers that we have with Mike. So the first and second models are in WaveWatch model. So they're surface viscous layer models by Tony Liu and Eric Muller Christensen, date back to 35 years ago. Assumes the ice is like a thin elastic sheet. The second model is like the first model, IC2, but it's got a scattering algorithm that Fabrice Adhem put into it around 2015 and published. And it depends on ice flow thickness, concentration, diameter. So it has some important, it needs to know what the ice conditions are. The third model is by Mike. It's Mylan 2014. It's already inside WaveWatch, and it's kind of a simplified, flexible, efficient scattering model based on a polynomial fit to field data. And it's got frequency-dependent attenuation, and it's got some rollover effect. Depends on ice concentration, but not flow thickness or size. And the last 3 models are what we put into the model. So the BIO model is kind of old. It's more than 25 years old, but it is based on sort of basic engineering kind of approach. It's based on a Boltzmann scattering integral. So think about scattering in modern physics. Its energy is redistributed directionally. It assumes rigid ice flows, and it can partially submerge the ice flows. It depends on flow size, thickness, and concentration. The 5th model is like the BIO model, but it assumes flexible ice flows, less scattering, and it conserves energy and accounts for some directional scattering. So it's derived from Malin and Bennett's 2018, Malin and Squire 1996, 97. And so we just denoted as MBS model here. And the 6th model is like MBS model, but it has more energy loss. And so it's denoted MBS prime. So those are the 6 models. And so what are the basic characteristics of these models? to answer the question, we assume a simple rectangular ocean with open water in the blue dots and ice in the yellow dots. And we assume the wind is from left to right, constant wind everywhere, and constant flows everywhere. So uniform flows everywhere. So there are some of the dimensions of the rectangular ocean. It's kind of large, 7,500 kilometers, grid spacing 5 kilometers, wind 20 meters per second. So if you go back to Perrie and Hu, 1996, when we did this little model, our model, the BIO model, is very sensitive to concentration. So if you increase the concentration of the ice, the attenuation ramps up, but it's not very sensitive to ice flow thickness. So talk about having the flows partially submerged is probably not really making much of a difference because the model's not very sensitive to that. But anyway, that's what it is. Low size, concentration, but not much on thickness. And so we compared these models and we did a simulation for a two-day run, 48-hour simulation. And so here are all the 6 models: BIO, the 2 IC2 models in WaveWatch, MBS, MBS prime, and Malin 14. And this is how they compare as a function of frequency. This is the attenuation. And attenuation is defined like radiation attenuation, dE dx over E. And so what we see here is IC2 behaves kind of interestingly, and I don't know how to explain that because it's not my model. But the other models kind of go up and either they flatten out like MBS prime, or they kind of roll over like some of these other models, but it's not a pronounced thing. What the big note to give you is how different these models are. So if you think about blowing the wind over the water, the waves grow, they reach the ice edge, and then they attenuate. So this is a log plot. And so there's a big difference between MBS model and IC2. It's orders of magnitude. So these models are really kind of radically different. And if you have good field data, we would hope you can identify which one is the best model. But that's easy to say, but it's hard to do. And there's some of the details about what the flows look like for this test. And this test has been published in JGR. And what's more interesting is slanting fetch case, because of course the wind is never perpendicular to the ice edge. The wind is always at an angle. So we did this case where the rectangular ocean has winds sort of at 45 degrees, and the ice edge is right along where the cursor is. And so I just looked at these 3 models, and what's interesting is the sort of turning effect. So as the waves enter the ice, they turn towards normal. And if you live in a place like Canada, you know that if you drive your car along the road and you hit a snowbank, the snow will tend to turn the car towards normal, just like these waves. So it's sort of like the classic refraction thing. MBS model is not as dissipative, so it turns, but also there's room for generation of waves inside the marginal ice zone, whereas that's not at all evident in MBS prime. This is more dissipation. And on the right side, you have some of the characteristics of significant wave height, attenuation, and the 2D spectrum as the waves propagate. I don't know there's anything to remark here. In the interest of time, I think I'll just keep going. We looked at 2-dimensional spectrum, and we can see some differences among the models. The main difference would probably be something about the magnitude of the peak energy in these different models, but qualitatively, they look similar. MBS model is a little bit more isotropic than some of the other models. And I think I'll keep going. So if you go further inside the ice edge, it becomes very isotropic. So here we are. These are the models. There is various characteristics you can see. We didn't have any ice breaking in these simulations. We didn't have any redistribution of the flows. The flows are held constant, so that's not like the real world. And there's a tendency to isotropy in some of the models. But to go farther, we need real storm cases. And so this comes to the sea-state boundary layer experiment that Jim Thompson led. And that's the schematic of some of the instruments in the water. And you can go to his website and find lots more information about this experiment. This is a movie that Eric Rogers made showing you the ship transect for 6 weeks as it moved around the ice. And what's interesting is here is a diversity of cases here. So sometimes, like now, the deployments are in more open water around October 14th, 15th, and the waves are kind of large. And later on, the deployments are near the ice edge, and the waves are moving at slanting fetch to the ice edge, like I just showed you in that ideal case. So let's keep going. Another issue is knowing the ice. So if you spend some time studying ocean waves, you might remember that back in the 1980s, when wave models were just emerging, the constant song that you would hear at meetings was, it's the wind, stupid. And that meant that people would say, well, the model's not working well because winds aren't very good. It's a nice way to escape the problem of maybe your model isn't very good. But in marginal ice zone, we have another problem, that's the ice. And so in boundary layer sea-state experiment, this is a comparison from one of the meetings at Stennis Space Center, must be somewhere back there 8 years ago. And it's comparing the ice models that were to inform the wave models. And what I only want to point out here is the diversity of ice model information. And so it's 20–40% difference. Okay, so coming to compare the model with the field data, we thought before we were starting this, okay, we'll just look for cases. We'll look for special cases where the buoys line up in a line and we can just pick out the waves, and lo and behold, we'll know how the attenuation works because it'll be just so clean and easy. But anybody who was in the field making an experiment would tell you the buoys always move. So they never stay in a line. They're always moving. And therefore, you have to output the model at the points of the buoys if you're going to make any comparison and if you're going to get any idea of which model is best. So I don't know why that kicked out. Here we are. The second part of this talk, we'll look at the results, and we're only going to look at 2 storms, the biggest storm, October 11th and 14th, and the slotting fetch case, 21st to 24th. And so in the top 3 plots, I plot concentration, thickness, and flow size, and the other 5 plots, I report 5 of the models.
Well, we can't see, we can only see the slides. I think you have to stop sharing and share your new slide.
Okay. That's different from Teams.
Yeah, it is a bit different. Yeah.
So in Teams, as long as it was there, you would see it. So I have to get out of this.
You just try. Well, if you click share entire screen when you go sharing, yeah. But stop sharing.
Stop sharing. I need to find that green button.
No, here
You got to stop sharing first of all. Well,
red
yeah.
button on top. Red option on top. Stop sharing.
Okay. Just trying to find that green button.
You can find a red option, red button on top. Yeah, now it is.
Yeah, I've stopped you sharing, well, but now start again and just go, when you click on share screen, share entire screen.
Yeah. Okay, share. So here I am. Good thing you stopped me.
Yeah.
Okay, let me go back. I'm just looking for the power, because if you spent a couple of decades doing ocean waves, ideal experiments like John Swap, you always look for the clean case. You always look for the case where the waves are perpendicular to the coast. The wind is perpendicular and blowing off the coast, and then you choose only a narrow window of winds perpendicular, and then you analyze the wave height, and then you can make fetch laws for growing waves. And so I thought, oh, let's just do the same here. We'll look for the two biggest storms that look somewhat clean, and that will show us which model's best. So the first storm was October 11th to 14th, and here are the buoys. And as I click through this storm, you see how the buoys move and how the models change. But the problem is there's very little ice. So the waves are very high, up to 4 meters, but there's very little ice. They seem to attenuate at the end. So what I did was I called this case 1, part 1, up to about October 13th, and then case 2, and case 1, part 2, where the waves are attenuating at the tail end of this. And the second case is October 23, 24, the slanting fetch case. And again, you can see how the buoys march along. And now we have a diversity of things. The buoys are loosely spread in terms of the waves they see. So this shows you the swath of wave heights for all the deployments. They grow, they reach a peak, and then they decay. They're only about 1.2 meters, but in the whole field experiment, these two periods were the two best ones in terms of having strong waves. So here, these are two storms, and the buoys are sometimes in open water with a little ice, like case 1, and case 2, we have diverse ice conditions. So let's have a closer look at this. So this is case 1 from the sea state experiment. There are photographs, so I can verify there really was ice. Not much, but there was some. And so ice concentration is very low, and that shows you the wind. So this is October 11th, 12th, and 13th. So you see how the system evolves and how the buoys move. And here's the waves. So the waves are indeed attenuating towards the end of it. And so for this plots, we're showing you the results from MBS prime, and we're using ephemer wind fields and ephemer ice conditions, because Fabrice was very kind and he lent us these fields. We didn't have any other way of generating them. For the part 2, for the decaying part of that case, there's a little more ice. You can see from the ice concentration. So this is October 13th at 6 hours, 15 hours, and October 14th. And the waves are turning and they're feeling the ice. So we have moderate to light ice conditions. Case 2 has heavier ice, and you can see from the photographs that it was heavier. Of course, the photograph is at the ship, and that might not be different. That is probably different from the location of the buoys, but qualitatively it tells you there is some ice around. And here are the buoys. So October 23rd, 24th, and you see the buoys are in more ice. So more ice conditions, and indeed the waves turn. So this is just like that ideal rectangular ocean case. It's sort of like it. The waves turn as they enter the ice edge towards normal to the ice. And so we're going to look at this in a little more detail. How to differentiate the ice models. So the first case, you have high waves and all the models line up. You can't differentiate them. They all look about the same. They're all doing well compared to the observed buoys. Towards the end of that case, there's attenuation going on, and the models separate out. So the difference between the BIO model, these deep blue dots, and MBS prime, and then green is MBS, and Mayan 14 is this one, sort of almost flat. And then Mayan 14 drops down to the bottom at this point. And then case 2, the crosswinds case, the sort of slanting case, it gives even more interesting diversity. So it's well scattered. And if you ignore the large scattering of the light blue dots, that's MBS prime, you could say they're kind of distributed over the diagonal, and that's a good thing. Whereas green MBS is kind of high, so it needs, you would say, more dissipation. And the BIL models down there, deep blue lines. So if you look at some of the statistics, it's not all giving you a clear message. Sort of light blue gives you the best statistics and yellow is the second best. So it looks like the MBS and the MBS prime models are doing well in terms of those statistics. So RMS error, bias, correlation, scatter index. But this is significant wave height. So significant wave height, it integrates over the angles and over the frequencies. So it hides all the discrepancies of the spectrum. It reduces the whole spectrum to one number. So we wanted to dig into that a little more. So these are directional buoys. So we spend time to get the directional spectrum. And when we started doing this, we didn't know quite how to do it. We had a couple of different methods for the observational buoys, and sometimes there are different answers. And we kept doing this until we got both methods to converge. So we really think we understand the directional spectrum from the buoys, and that's the two plots where the cursor is. And here are the models. And up here is the corresponding 1D spectrum and the corresponding HS. This exercise didn't give me what I wanted. It didn't sort of shout out, here's the best model, because oftentimes what's happening is wave heights are increasing, that's the red line, whereas the models are either flat or they're decreasing. So it's the opposite direction. If you look at the 1D spectrum, it's different between observed and models, and it's very different. And if you click through this, as the black dot shows you where we are, as you click through this, it doesn't change a lot. The red curve is, if you like, the truth, it's the observation, and the models are like that. You might say they're kind of similar, but it's not as good as I would have hoped. But again, there are errors in the winds, there are errors in the ice, so maybe it's as good as the models are ever going to get. The models among themselves
Excuse
have
me,
some.
you are having
Yes,
2 more minutes.
I
You are
can't
having,
hear you.
yeah, okay, thank you.
Is it
You
okay?
have 2 more minutes.
Okay, I'm going to wrap up quickly. So I won't go over this much more. We did lots of studies about the 2D spectrum. We didn't get quite the answer we wanted, and I suppose we're still kind of thinking about that. So this is case 2. So the final thing we looked at was attenuation, because attenuation is what we looked at way back years ago and with the BIO model. So here's case 1. So case 1, there's very little ice, and all the models line up well. The energy looks very similar in all the models, and the attenuation of the models is this flat line right in the middle, whereas the buoys are a little bit scattering around it. They actually see ice, but we didn't get it because the ice and wind conditions said there wasn't any. So case 1 isn't able to differentiate it. But the second part of case where we have some attenuation, MBS prime qualitatively can capture what's going on in the instrument. So this is looking at attenuation between 2 deployments. That's what this is. So green is one calculation, blue is another. So MBS prime does better than the other models. That's my message to you. And so case 2, we get more of that. So here's case 2, the slanting fetch case, the sort of demanding case. And I'm always kind of thrilled by MBS prime because it could match all the different combinations of buoys in terms of their attenuation, and it did better than the other models. So that's about what I got to. When there's no ice, the models all look good, and that's a good thing. They should. And when there is ice present, it looks like MBS prime is the one to put your money on. Thank you.
Thank you. We have time for some short questions. We are running out of time. Any question?
I'll just
Yeah.
make it maybe more of a comment. Well,
Yeah.
You
which
can disagree, Mike.
I don't want to put any money on anything. I've made some money on betting on the cricket. I'll just stick with that. But it looks really interesting. There's certainly you've done a lot of great work here, that's for sure. Yeah, I'd love to see it. And a lot of this is new to me. But I think that it's interesting, even working out what's the best, we need more measurements, and we need to understand from what you've done, like what is the best, would you say, what's the best measurement? What's the best experiment to do? Do you want to experiment in a big storm? Do you want to experiment in the right ice? What would you think? Just trying to promote.
These models all have so many assumptions in them. For example, a BIO model, circular ice flows, all the same. And so we put in the ice information that we got, but probably, I just don't know. Probably the first thing would be to be more certain about what the ice conditions were. So I showed you way back a few slides ago the diversity of ice forecasts, and we just chose EFMR because that's the data that Fabrice gave us. But I'm sure that that's not perfect either. And had we chosen Max Planck data or maybe NOAA data, the answer might not be quite the same. So for one thing, just knowing the wind and the ice conditions better. So always we know the conditions at the ship because they're observed, but these models, then we have to implement the model for 1,000 or 2,000 kilometers. So beyond the ship, we're just relying on what the Met Service is giving us. And so there could be big biases there. I wish I understood better how to interpret the 2D and the 1D spectrum. So we did this calculation, and I feel kind of unsatisfied with my inability to use that information to identify the differences in the models. But then if you go back, there should be big differences. The attenuation plots that I showed you way back near the top, the start of the talk. And so there should be big differences, but I couldn't find them in the 1D and 2D model outputs. So I guess it was still not sure quite how to proceed on that. Sorry if I wasn't helping here.
Well, yeah, it sounds very interesting. I mean, I think we're almost going to start the next talk, but Bash, did you have something you wanted to say quickly?
I'm sorry?
Bash, I know Bash had his hand up.
Oh, yeah, I was going to say, like, the summary says it all. The wind looks fine. When you don't have ice, it seems like the wave height agrees with the observation. But the input wind is not what the boys sitting in the ice sees. I mean, the two are different. And that's the real problem, the errors in the input wind field. And that's been a problem. And so we don't know what the input wind. I did play a little bit fiddling with the 3 input components by adding or reducing the input by 20%. And there was a case where we did better. But then again, we don't want to go into tuning the input ice field. So again, it's all in the ice, input ice.
But we don't want to admit to tuning.
Exactly, yeah.
All right. I think, Susan, we need to move on. Is that right?
Thank you.
Thank you very much,
Yes.
Will.
We should go for next